Hello and welcome. Today we're going to be talking about the multivariate chain rule. To start this off, I think it's good to revisit the regular chain rule. In one variable, we have the following. If you have y is equal to f of x, right? And then you have g of x as well. What you can do is actually say that y is equal to f of g of x. You can have a composition of two functions. Now, of course, if you have dy dx, what you do is you write f prime of g of x times g prime of x. Another way to write this is df dg dg dx. And this, the product of these two things, then allow you to compute that that derivative that you want to compute. So the question then, of course, is we want to be able to do a similar thing. We want to do a similar thing in two dimensions, i.e. we have an x and a y, right? So we're going to consider now, we're going to consider a trajectory. So we have r of t is equal to x of t, y of t, like that, right? And we're also going to consider a surface. So we have z is equal to f of x, comma y. We put them together. We have z of t is equal to f of x of t, y of t, right? And the goal is to compute dz dt. It's probably good to get a picture of what we're talking about here and why this is important. So we want to know how to compute that, but let's try to figure out this thing. All right, consider x of t and y of t as essentially a path on a flat map. Okay, so we can consider it like this. There's x and there's y, and we have our trajectory, our x of t, y of t, as being some pathway that's on this flat surface. But when we go to the z-coordinate, we can now, so on this map, think of it like a hiking trail. But we all know that hiking trails aren't flat, even though the map itself is a flat thing. When you're directed to go along a pathway on a map, you know there's going to be ups and downs. So we can define the surface like this. All right, and of course, as I project up, I can find that point on the surface that corresponds to the going up and the going down. As follows, like that. Okay. So that's the idea. And of course, I know that while I'm on this, so the surface, of course, is like that. You can imagine that it has lots of ups and downs and undulations. And of course, just like a mountain, you have there might be peaks and valleys and all sorts of stuff on the terrain that you want to navigate. But when you go on a trail, you're going on a specific pathway within those peaks and valleys. And we want to know basically dz dt is going to be basically the rate of ascent or descent or descent on that trail while you're on that trail, hiking on that trail. All right. So in addition to this, so how are we going to figure this out? Now if I'm at this specific point, now I'm pointing at a very specific spot. So I'm here at x of t, y of t, right? I know I can always put in a tangent plane. A tangent plane that's at x of t, y of t. All right, so of course I would draw that tangent plane. Let's figure out that tangent plane. We know that z is going to be equal to z naught plus the partial derivative of f. I shouldn't say that. Hold on one second. I'm going to go back up. I'm doing maybe slightly bad notation here. This is going to be z of t times partial derivative of f with respect to x, evaluated at the point x of t, y of t, times x minus x of t, okay? And then we're also going to have plus the partial derivative of f with respect to y, evaluated at x of t, y of t, and then times y minus y of t. Okay, think of these as basically variables right there. Okay, x and y. Right, so what I want to do now is I want to think of this as basically, where am I going? If I'm right here, if I'm at that specific spot right there, but then as I go on my trajectory, I'm going to end up at a new space right there, right? So I'm not just going anywhere in the xy direction, I'm going on a specific spot. And that spot, of course, is going to be x of t plus delta t, and y of t plus delta t at some later point. Okay, and I want to know what the gain is in z, how much z changed as I changed delta t. So what I can do is, what I'm going to do is, I'm actually going to put, that is going to be my x of t plus delta t. And that right there is going to be my y of t plus delta t right there. So y at a little bit later point. Okay. And then I want to know where my z is, and that's going to become z at t plus delta t. Okay, so not only am I going to find a specific point on my tangent plane, I'm going to find out a specific point as I go further and further away from that where this tangent plane is tangent to the surface. Okay. All right. With this stated, let me now I'm going to go select this just real quick. I'm going to go to the next page, like this. All right, and now what I'm going to do is I'm going to rewrite this. I'm going to actually call z of t plus delta t minus z. Okay, we know we can call that's delta z, right? And this right here, this expression is clearly going to be delta x. And that expression, that's going to be delta y. Okay, so if I rewrite this as delta z is equal to the partial derivative of f evaluated at x, evaluated at my original point, okay, and then multiplied by delta x, okay, plus the partial derivative of f with respect to y, x of t, y of t, okay, we're still starting at that one specific point, and then we're changing a little bit in the delta y direction, okay, as we go along our new path. Okay, well now all I have to do is divide by delta t. We can do that everywhere. And then of course take delta t to 0, and what we get is dz, where I should actually, let's back up here for a second. I'm not taking delta t to 0, I'm taking it to an infinitesimal, in which case we're going to get dz dt is equal to, and the partial derivatives here, they're just hanging out. They're not doing anything. Multiplied by dx dt. This is what that becomes. plus, and then we have, we have a partial derivative of f with respect to y times dy dt. This right here is the multivariate chain rule. So this is the formula we're going to remember in order to compute basically my rate of ascent as I travel across a surface on a particular trajectory. All right, so the thing I think we should do next is we should do an example. Well, so let's do that. Let's go to the next page, and I'm going to talk about a specific trajectory. Let's do a circle. The x of t, y of t. And it's going to be equal to cosine of t, sine of t. All right. So, and then what is the surface? It's going to be a hyperbolic paraboloid. Hyperbolic paraboloid can be defined as z is equal to x squared minus y squared. That's a particular hyperbolic paraboloid. Right? So that's going to be my f of x comma y. Right? So of course we have z of t is equal to f of cosine of t sine of t. Right? And I want to compute what dz dt is. I want to know what its rate of ascent is. All right. So I'm going to actually, let's just go out and do it. We need all those pieces. We need the partial derivative of f with respect to x times x prime, plus partial derivative of y with respect to, partial derivative of f with respect to y times y prime. All right, so let's get all these things together. Partial derivative of f with respect to x, that's going to be 2x. Partial derivative of f with respect to y, that's going to be negative 2y. Okay, finally, then we have a dx dt, otherwise known as x prime. That's going to be negative sine t. Cool. Right, and finally we have a dy dt, and that's going to be equal to cosine of t. All right, we have all our pieces. Now let's assemble. But we just have to remember we're evaluating the partial derivatives on the particular point of the circle that we're at. So what we're going to get is dz dt is equal to 2 times x, and x is equal to cosine of t, times negative sine of t. And then we have now a plus negative 2y, and y is equal to sine of t times cosine of t. Of course, we forgot the negative there. I'm sorry about that. We have to put that negative on the 2 sine t. Okay, so that looks good. These are actually like terms, so we can combine them together to get negative 2 times 2 cosine of t sine of t. And this is actually a fairly recognizable trig identity, negative 2 times sine 2t. That's what we have there. All right, so let's see if we can get a picture of what this thing looks like. So it turns out the hyperbolic paraboloid that we have here, that's actually what they call the Pringle shape. That's the Pringle surface. So if I were to draw it, there's my x, there's my y, and there's my z. The surface is going to have an upward facing parabola in the y equals 0 plane, and a downward facing parabola in the x equals 0 plane. Right? And as we go around the circle, it's going to start down. It's going to start up here, and it's going to head down, and then go back up. And then go down, and then head back up, like that. What we see here is there are actually 2 ups, and then there's also 2 downs for any t going from 0 all the way to 2 pi. Anytime we go around a full circle. Notice this has that. So basically it's going, there are 2 ups and 2 downs along t going from 0 all the way to 2 pi. So our formula for dz dt does reflect the fact that this Pringle shape, essentially you're climbing 2 mountains to 2 peaks, and you're also going down to 2 kind of low points as you go around every 2 pi interval. Okay, so I hope that gives you a good example of how you can use the multivariate chain rule to compute something like this. Thank you very much.